All right, let's dive into the invisible rhythm. We're going to do a crash course on AC circuits. We're going to talk about the magic that powers basically everything around us, how a single wire can carry a whole symphony, and how our lights just work. It all comes down to alternating current. I mean, really think about this for a second. How on earth does one single wire from an amplifier create this rich soundscape with all the highs and lows? You've got the deep thump of a bass drum and the sharp crack of a cymbal, all traveling together. The secret? Well, it's all about understanding the language of alternating current.
So to really wrap our heads around AC, it actually helps to first talk about what it isn't. And that means we need to take a quick look at its simpler cousin, direct current, or DC.
Okay, so DC, think of it like a one-way street. The electricity just flows in one constant direction. Simple, right? But AC, well, that's a whole different ballgame. It's more like a busy two-way street where the current is constantly flipping back and forth. And it's this back and forth rhythm that gives AC a super important property DC just doesn't have: phase. And trust me, that's where things start to get really interesting.
And the most fundamental, the purest form of this rhythm is the sine wave. This is the absolute basic building block for every AC signal. I'm talking about the power coming out of your outlets, the radio waves carrying your favorite song. It all starts with this.
So if we're going to get this, we really need to learn the language of these waves. There are basically three key specs that describe any sine wave. Once you get these three things down, you'll have the key to understanding how AC circuits actually work. First up, we've got amplitude. Super simple. It's just the peak intensity of the wave. Think of it as the wave's height. In electrical terms, that's its peak voltage or current. Basically, how loud is the signal.
All right, next step is frequency. This is all about speed. It's how often the wave repeats itself per second. We measure it in hertz or hertz, and the easiest way to think about this is with music, right? Frequency is what we hear as pitch. A low frequency is that deep bass note, and a high frequency is that sharp treble note.
And now for the one that can be a little tricky, but it is absolutely crucial: phase. Phase is all about timing. It's the offset. Are two waves perfectly in sync, or is one lagging just a little bit behind the other? You got to understand, in the world of AC, this timing relationship, it's everything.
Okay, so we've got this dynamic, constantly changing current. But what happens when we try to put the brakes on it? In the simple world of DC, you just have resistance. But with AC, the way we slow down current is a much more interesting story.
Let's just stop and think about that for a second. If your current is always changing, always flipping directions, does it make sense that a simple roadblock like resistance is the whole picture? No way. As it turns out, there's way more going on.
So, in AC circuits, we don't just talk about resistance. We talk about impedance, which we write down as a Z. This is the total opposition to current, and it's made up of three different forces that are all competing with each other.
So here are the three parts of impedance. First, you've got good old resistance. We know that guy. He's just a simple roadblock. But then you have two new players in the game: inductive reactance and capacitive reactance. Inductors, those are coils. Think of them like a heavy flywheel. It resists change, so it causes the current to lag behind the voltage. Capacitors, on the other hand, are like a spring. They react instantly and then push back, causing the current to get ahead, to lead the voltage. These two new forces, these reactances, they're not just roadblocks. They mess with the timing.
And this right here brings us to one of the most important takeaways. AC quantities aren't just simple numbers. They are vectors. That means they have a magnitude, like how strong they are, but they also have a direction, or what we call a phase. You can't just add them up like 2 plus 2. You have to treat them like forces, all pulling in slightly different directions.
Okay, so you've got all these competing forces, all these timing shifts. How in the world do you figure out what's actually happening in a circuit? Well, the answer is you have to draw a picture. You have to visualize it. And the tool we use for that is something called a phasor diagram. It's just a genius way of taking all that complex information, the magnitude, the phase angle of every voltage and current, and turning it into a simple drawing with arrows. And boom, here it is. This is the aha moment. Look at this diagram. See how the resistor's voltage and the capacitor's voltage are pointing in different directions? They are 90 degrees out of phase. That means you can't just add their numbers together. You have to add them like you would forces, head to tail. It's literally a tug of war, and the main input voltage is the final result of that battle.
Now this whole idea of adding waves together, that's the key to our original speaker mystery. A real sound, like from a violin or a drum, isn't just one pure sine wave. No, it's a complex mess. But
You can build that complex wave by starting with one fundamental wave and just adding on a bunch of smaller, faster waves called harmonics. You keep adding them up, and you can create literally any sound you can imagine.
Okay, so let's bring this all home. We've talked about waves, phase, and impedance. So what? How does this actually explain that loudspeaker? And, power our entire world? Let's get to the payoff.
And here's the magic, right inside the speaker. It's a circuit called a crossover, and what it does is brilliant. It uses an inductor, which, remember, resists high frequencies more, to send all the low-frequency bass sounds to the big woofer, and it uses a capacitor, which resists low frequencies, to send all the high-frequency treble sounds to the little tweeter. It's basically a traffic cop for frequencies, directing everything to exactly where it needs to go.
And seriously, this isn't just for speakers. These ideas are everywhere. The entire power grid relies on this stuff. Power companies have to install huge capacitor banks just to cancel out the inductive lag from all the motors in a city, making the whole grid more efficient. Getting a clean radio signal? That's all about something called impedance matching. It is absolutely fundamental to modern tech.
And check this out. This awesome 3D plot shows you that concept of matching perfectly. That massive peak right in the middle, that's the sweet spot. That's where the impedance of the load, like a speaker, perfectly matches the source, like an amp. And when that happens, you get maximum power transfer. You get the most bang for your buck, the most energy sent where you want it to go.
And, this isn't just abstract math on a whiteboard. This is what engineers do every single day. They use tools like function generators to create these waves, and then they use oscilloscopes to actually see them, to measure that invisible rhythm and make sure every single part of the circuit is doing exactly what it's supposed to. So I guess the crucial point to take away from all this is AC isn't just electricity being on or off. It's a language of timing, of rhythm, of vectors and forces all interacting. And it's that beautiful hidden complexity that lets one little wire carry an entire orchestra. So yeah, AC circuits really are the hidden language of our modern world. It's this invisible, rhythmic dance of electrons that makes almost everything we rely on possible. And now that you can see the patterns, now that you know a few of the steps, what else do you think this language can explain?